My name is Nico, and this is the Column Store in the Batch Execution Mode video series. Welcome to the very first episode. This episode is focused on something that is dear to the heart of every single DBA or database caretaker, as I call other people who are, have to take care of their databases, instances, and services. So what am I talking about? I'm talking about the maintenance. The maintenance? Yes, the maintenance. Some people talk about the raw store indexes maintenance in the way that they say it should be done. Some other people argue that, well, you spend a couple of hours and you practically get no results. But in the column store indexes world, I think there should be virtually no conversation about the necessity or the will of doing the maintenance. It's only the necessity. You gotta keep taking care about your column store indexes, because if for the row store indexes, once we delete a row, we mark the row for deletion and a single row will be removed. The other situation is for the column store indexes. When we are deleting a row, and this row is to be found not in the Delta store, not in the tail row group for the in-memory column store indexes, when it is there, it's physically deleted like for the traditional row store indexes, because the Delta stores other row store structures. But when we are deleting a row within the compressed row groups, we're using the deleted bitmap structure to mark this row as deleted. And this is where the problems start to take place. And let me take you for a ride. I'll show you a couple of the situations, and I hope you will believe me that even if you're running the latest and the greatest SQL Server 2017, or you just playing with CDPs of 2019 right now in November of 2018, it's the latest and greatest available. If you're running Azure SQL DB, if you're running Azure Managed Instance, you still need to do the maintenance. If you will not, there will be scary results. As I have seen, over 98% of the whole table being marked as deleted, and nobody took care because people simply believe that it's done automatically. I'll tell you, there are no unicorns. Well, follow me. I'll show you a couple of examples why you need to take care of your column store indexes. Follow me. Here I am using the SQL Server 2019 CTP 2.1, as you can see here. I will be creating a rather simple table here, which I will call row group testing table. First, I will ensure that this table does not exist. Then I will create the table with just one single integer column and the clustered columnstore index. This is the inline definition, which is available since 2016 version of the SQL Server. Next thing, let's load just simple 5 row groups, which means, well, around 5.2 million rows. This is part of the script. We'll do this. It takes a couple of seconds. After the execution finishes, and it took exactly 2 seconds on my virtual machine, I'm ready to take a look at what is going on with the row groups. And if I look and execute using the CISL function from my library, open store and available on the GitHub, check out the link on your screen. If I run the CStore get row group details function, as you can see, I will get the full list of the row groups, and you can see their IDs, their status, compressed number of rows, and most importantly, how many rows are deleted in this case. All right, so we've got perfect row group with nothing deleted yet. Next thing, I will run the same library, same open source library CISL, the get fragmentation function with the parameter of the table name and indicating that I just don't need similar tables but just this one. And you can see that there is logical fragmentation. The number of rows within the deleted bitmaps is 0. There are no fully deleted row groups. There are no trimmed row groups, which makes perfect sense. And here you see the total number of rows, 5,242,880. Everything is fine. Everything is beautiful. So let's do something funny here. Let's go and delete the first 100,000 rows from our testing table. Let's run the query, and after a couple of seconds, if we go back and check on the row group structure with the same function we used before, we should be able to notice that indeed the very first row group with the row group ID 0 contains 100,000 rows which are marked as deleted, right? Okay, seems like nothing too big, nothing to worry about. That's it. Well, you know what? I would like to use that advanced capability of the SQL Server, which allows us to do a self-merging operation, which means basically I would like to recompress the very first row group on the basis that, I want to see that it will have not 1,048,576, but 948,576. So, you know, I don't want to process 100,000 rows extra, a kind of a penalty every time. So I will run an outer index reorganize command, as you can see on your screen. And I will use a supported and documented hint, which is called compress all row groups on, which will, will do some extra. Even if there are some open delta stores, it will find and compress them. In any case, after the ETL process, involving the column store indexes, I am making sure that no delta stores are left behind, and I'm running this statement with a hint practically always. So let's execute the statement a couple of times, 3, 4, 5. Well, should be enough. Let's check out on our internal structure. Anything happened? Well, breaking news. We didn't hit on the threshold for recompressing the row group. And this means that in this case, this row group will not be considered as feasible for self-merge, which means those 100,000 rows will stay ad hoc forever, unless, of course, we will find some very small row group with like maybe under 100,000 rows, and inter-row group merge will take place. Otherwise, we'll limit it, and that's not a very good news. So let's go back to the data deletion, and let's delete 100,000 rows in second and third row groups as well. And you can see the statements, what I am exactly doing. So coming back here to the to the row group details, we can see that we just achieved exactly what we wanted. 300,000 rows are deleted. So in the sum starts to, become an interesting amount. Let's see what kind of the fragmentation we have achieved with the get fragmentation function. Well, overall, on this table we already deleted over 5.72% of the rows. And I would say maybe in some cases, if we're talking about the huge tables, well, we might want to do some maintenance. But the thing is, because the number of rows for these row groups, as you have seen, and I'm coming back here, they are all under the threshold. No matter how often I will try to recompress or self-merge or inter-row group merge those tables, those row groups, I'm sorry, nothing will happen. Nothing at all. They will stay ad hoc forever until I will execute the command alter index rebuild on this table or on this partition. So that's the reason number one why you should be doing the maintenance, and you should be considering running rebuild on your column store indexes. Of course, after you decide that is needed, after you understand how much resources you will spend on this operation. Welcome to the second demo. In this one, I will focus on the very well-known and very well-respected functionality of the column store indexes, starting with SQL Server 2016, which is called inter-row group merge. This functionality is focusing on merging together different row groups which have enough row to form a new row group. So let's dive into the interesting cases of it. First of all, we are back using the 2019 CDP 2.1 SQL Server, as you can see here. And I'm still creating the same row group testing table with just one column and a clustered column store index, loading 5 row groups into the content of this table. We're done in just 3 seconds. Using the same CISL functions for the get row group details, we can clearly see that we've got 5 different row groups. All of them are compressed, and we have total rows, the maximum allowed number currently, with no deleted rows at all. Okay, everything is perfect. So let's go here and do something fun with it. Let's delete 448,576 rows from the very first row group. Then let's do the same for the second one and then for the third one. Effectively, what we will achieve with this operation is that we will have around 600,000 rows, and actually precisely 600,000 rows within every single row group of the first 3. If we take a look with the same function, you can see that the first 3 row groups exactly suffered the logical fragmentation. So we put this information into the deleted bitmap. All right. If we take a look at the fragmentation, we are talking right now about some serious fragmentation here. We have a 1/4, so over 25%, 1 in every 4 rows in our table are deleted. So we need to do something about it. So what can we do? We run the same alter index reorganize. And it is expected that the announce already, and in the documentation available, the aggressive tuple mover will do this for us under certain circumstances, on which I will not be diving today. But let's say it happens, we do it by ourselves, or SQL Server is executing this process on the background. So run it the first time, I rerun both of the queries, and what happened? We can see that the self-merge operation did kick in this case, because we are way below the threshold, and the first three row groups, they become something that is called tombstone, which means basically already deleted structure will not be used, will be ignored by everybody. We have three new row groups with IDs 5, 6, and 7. Remember, it all starts with 0. And we have 600,000 rows in them. We have 0% of the logical fragmentation. Sounds good? Yeah. But wait a second. Can't we rebalance this? I mean, doesn't look very good. It's actually will be not very productive for the query optimizer to process it. And we've got three row groups which are trimmed. And our average number of rows is this, so I would say I would like to have around 800,000 rows in every single row group. How can I achieve that? Well, the only way to achieve that is actually by using outer index rebuild. Because if I go back, outer index reorganize, and rerun again the same operation a couple of times, 3, 4, 5, whatever, coming back here will show me that I am actually stuck with those three row groups because they are too big to get the inter-row group merge operation. Because in the sum they would be overflowing the 1,048,576 row. Any two of them will create a combination of 1.2 million rows. And if I go and load more, 5 more row groups into our column store index, looking at it will start showing like we have a pretty disbalanced structure which will start affecting our performance. And if our performance is the paramount, we better take care of it. And the only way in this case to solve this is to run the outer index rebuild operation. So if I go here and we'll simply run the rebuild, you will see that the result will be very different from what we have. And we might be having even the small row groups at the end. Let's run this query. You can see now that actually we have a pretty impressive result here. You can see that I have the perfect row groups for the first 8 of them, and the 9th, the residual row group, it stays with this number, 751,424 rows. But it just won. The damage, or let's say the failure of delivering the highest possible performance is minimized, and maybe we'll be able to merge it after all later. So do not expect that inter-row group merge will solve all of your problems, because it won't. Another important addition to the already shown demo is pointing that in the previous version of SQL Server, specifically for the SQL Server 2016, when you are creating the row group that's suffering under memory pressure, as not enough memory to create the full row group, and the row group is trimmed, as described here in the column store indexes part 113 on my blog. If you are under memory pressure, your outer index reorganize will not be able to do inter-row group merge at all in 2016, in 2017, or in 2019, and of course Azure SQL DB and a managed instance. The other thing which is specific, very specific to 2016, is the dictionary pressure. Under dictionary pressure in 2016, no inter-row group merge will take place at all. And this has been fixed for 2017, but unfortunately so far the fix has not been ported back to 2016. So if you are running 2016, please be aware of both of these limitations. And I can tell you that I have seen in the wild a table with huge amounts of rows which had over 98% of the row groups marked as completely deleted but suffering dictionary pressure. And while the people were expecting the outer index reorganized to solve all of their problems, well, in the reality they were not checking if the row groups became removed after being completed deleted. So stay aware and please do not forget that the maintenance is really important. It will not go away just because you expect it. Demo 3 time. This time we're focusing on the lobs. Everybody loves the lobs. Everybody's keep talking about the lobs and how beautiful they are and how they would never ever use them in the data warehouse or, for the matter of fact, in the relational database at all. But I will keep on finding some tables which are called lob something and they're using varchar max, var binary max or and varchar max data types. So let's recreate this table which will contain one single column as the identity and a lob column. And then let's insert the maximum allowed number of rows into our table. I just did it because it took me over 38 seconds. Precisely, it's 39 seconds the time that I spent inserting this data. So it's done and it should be around perfect. Let's check on it with the CISL get row group detail function and the get fragmentation function. You can see, first of all, that we have not one but three different row groups, and the number of rows is pretty interesting because the first two row groups are trimmed because of their dictionary size. Oh, that's impressive. And then the last one is trimmed because of the bulk load and has ridiculous 298 rows. Pretty miserable, I would say, but well, that's what we have and that's fine. So let's do and run some queries on it. Let's delete 100,000 rows in the first row group. Let's check on the results. Well, we've got it. Congratulations. Yes, we've got almost 20% of our first row group which is deleted. Great. So now we should be able to do a maintenance. This is a SQL Server 2019. Dictionary size, who cares? And the overall fragmentation is still pretty low, but we still want to do the aggressive tuple mover thingy. So let's run it. Once, twice, 3, 4, 5, 6, 7, whatever. Did you notice that it was fast? Well, because nothing happened. Because nothing happened at all. You cannot expect this situation with lobs to be resolved automatically. Well, that's a pity, you might say. Well, I would never use a blob. Well, maybe somebody else will do that for you, and they will not tell that. You know, these things sometimes happen in IT. So you might say, well, but I will determine based on the size of the deleted rows and the fragmentation percent I'm using the correct function. I will find out, I will do a rebuild. Well, let's say you will do the rebuild based only on the 15%. When more than 50% of the rows are deleted, then you will do the maintenance. So what if I go and update just one single row with 1 million characters. Takes a couple of seconds, actually not even one, but well, I created one row which is huge, which is absolutely huge. And what should I do? What should I do? Let's delete the row. Now, what I have is a question. How do you measure that this row group is desperately needing to be rebuilt? Why? Because we have one single row which is absolutely and disastrously waiting for a rebuild operation. But the thing is, no matter how frequently I will run my maintenance, I have an open delta store as a bonus for some reason, and this size here right now is not correct because it doesn't include an overall storage for this row. So if you are running lobs in row indexes, in traditional indexes, you delete them and that's fine. They will be eventually physically removed. But if you are running the column store indexes, you need to find those heavy rows and you will need to force a rebuild in order to get rid of them. Even if they are quantifically represent just a few, just a couple of rows, they can have a huge size associated with them. So you better watch out when you, do and execute the maintenance. Well, that's it. I hope you have enjoyed the demos. I hope you agree with me that the column store indexes maintenance is absolutely important unless you enjoy having your databases becoming slower and slower and slower. Well, I guess there are not many of these people around. In any case, thank you very much for your attention and see you in the next episode of the column store and the batch execution mode. Cheers. Bye bye.